Hi there, folks, and welcome back. I hope you enjoyed the video concerning the squares being removed from all the golden rectangles to produce golden rectangles once again. And I thought perhaps what we should do is talk a little bit more about that in a lot of different ways, but I would like to first visit the concept of looking at similar figures such as the triangles you see before you right now, and talk about something else in relation to them, which might be helpful to you understand the situation with the golden rectangles. If we have a figure here with a side A here and a side M over here, and the other triangle similar to it, we go back to it again. If this is side X and this is side M, excuse me, can't have another M, can we? So I better change that. So let's change that to a Y, okay? Then we can write, because these two triangles are similar, we can write the following proportion, which states that if you compare A to its correspondent in the larger triangle M, and if you do a comparison of that to the side X compared to its correspondent Y, they should give you the same ratio because, of course, these are similar triangles. But what's kind of neat to look at is, you recall, if we had a proportion like this in 7th grade or 8th grade, 2:3 as 4:X, and you wanted to solve it, you could cross multiply to solve for the value of X by multiplying across this way, multiplying across that way, and of course you would get 2x over here, and you would get 4 times 3 over here, which is 12, and you would divide each side by 2 to get x equals 6. So you know 2 compared to 3 is the same as 4 compared to the answer we got, 6. Well, here's something else you should notice. In that same proportion, 2:3, 4:6, we could reverse the order of the 3 and 4, and we would still be able to cross multiply and get 12, right? And they both would be 12. 2 times 6 is 12, 4 times 3 is 12. So we can do this and replace the 4 with where the 3 was and the 3 where the 4 was, and notice we still get equivalent ratios. Well, what am I trying to mention here? What I'm trying to show you is that when you have similar figures, if you compare two sides in the same order in one figure, and you compare the two sides in the same order in the other figure, that is A to X and M to Y, you realize that they should be the same ratio. And that's exactly what happens in golden rectangles. In golden rectangles, okay, the corresponding sides are the length and width, and when you compare them in both of the golden rectangles, you will always get phi. So you have to also understand that the length compared to the width in a rectangle that is similar to another rectangle who has length and width, the ratio should be the same. And of course, for the golden ratio, or for the golden rectangles, it is the golden ratio that we're talking about. Okay, so with that in mind, let's go on. Okay, sorry about all the clocks ringing. It's 6 o'clock here, and they're all going to ring. Sorry about that, but what are you going to do? All right, let's review very quickly what we talked about in the last video. What Dr. Ed talked about was the fact that if you have a golden rectangle such as this large one, and you take out the largest possible square, which I'm going to kind of highlight in blue, okay? If you take it out, the rectangle that's left over, the red one, is also a golden rectangle, because if you compare its length to its width, you will also get phi, the golden ratio, okay? Now, before we go any further, I would like to show the very end of that video again, if I can make it work here, and show you how in the cartoon back in 1958, they lined up all the golden rectangles to infinity, and they showed that in a drawing in the cartoon, and I thought that was kind of cool the way they did that. We are going to take a look at that, okay? And so I'm going to switch over to that.
It's a most remarkable shape. It can mathematically reproduce itself indefinitely. All these rectangles have exactly the same proportions. This figure also contains a magic spiral that repeats the proportions of the golden section into infinity.
And of course, that's the image I think is so fantastic right there, all those golden rectangles lined up. Okay, so now we'll switch back, all right? The question I have that I'd like to ask you now is if we can take all those rectangles like that and get them by removing the largest square from a golden rectangle to produce another golden rectangle. I wonder if we could go in the opposite direction. I wonder if we could take a small golden rectangle and on its longest side add the largest possible square. Would that form a new golden rectangle? And then to that golden rectangle, add another square to its length, on its length side, that is, and would we get another golden rectangle, and so forth. Could we continue this process over and over again? So if you would take a look, please, at your sheet, which is called Group Work 19, look at the second page of it, you'll see a figure that looks like what you see over here, okay? Now what I'm going to do is I'm going to make this very small on my screen so that you can see it very easily, okay? Now, I know it's kind of small, but it'll give us the idea of what we want. Down here in the lower section of the figure, there is a small golden rectangle, and you might not be able to read it at this point, but what I'm going to do is I'm going to do this. I'm going to take the view back up again a little bit, make it a little bit larger, and then I'll let you see that down here is the golden rectangle, okay? I'm going to color that in blue. Now, just in case the sheet you got is not correct, would you please put in the point D, X, C, R over here, okay? And make sure you have those points in there so when I talk about them, you'll know what I'm talking about and what their locations are. Now, YMCX is a golden rectangle. You can see it. Its width is 2. You can see that over here. Its length is 1 plus square root of 5. What if I add the largest square I possibly could to that figure? Well, I'm contending we should have another golden rectangle. RTCX should be a golden rectangle. All right? Well, let's assume that it is and that I'm not lying to you. All right? Well, let's see if we can figure out what the dimensions would be of that rectangle. From T to M, Y to M, R to Y, and R to T, we've got a square, right? Well, how long is that square? Well, if you look at this figure carefully, isn't it 1 plus the square root of 5? It's exactly the same as what's on the bottom of YMCX. So this would be 1 plus the square root of 5. And this would be 1 plus the square root of 5. Now, that's the case, all right? How long is it from T to C? Well, it would be 2, the distance from M to C, plus 1 plus square root of 5, which is the distance from M up to T. So how can I put those two together? Well, if you remember your algebra from maybe your junior year in high school, you can add the 2 and 1 together because they're not under or near the radical sign. So that distance from T to C would be 3 plus radical 5. And I'm going to add that to the figure, but I'm going to add it to the other end of the figure over where f to d are. So in other words, I'm going to write it here. 3 plus radical 5. Now, why do I know I can add that there? Well, the light gray square happens to be the largest square that I could add to RTCX, which is hopefully or supposedly a golden rectangle. So it's the largest square I could add to it. Since it is a square, it has to have the same dimensions as that T to C has. Okay? Well, that's interesting. If that's 3 plus radical 5, what is FR? Wouldn't it be 3 plus radical 5? Now, if that's 3 radical 5, from here to here is 3 radical 5. If this is 1 plus radical 5, 3 plus radical 5 was the other distance, the two put together should be what? Well, I can add the 3 and 1 together by algebra. So that's 4 plus, and what's a radical 5 and another radical 5 added together? Well, it's 2 of them, right? So that's 2 radical 5s. Now, what I'm going to do is I'm going to make the figure very small again so that we can take a look at the whole figure on your sheet. So I'm going to change my view back to 75%. I'm going to move it up. All my dimensions are still there. So if that's 4 plus 2 radical 5 right there, okay, all right. Well, let's see. That's the largest square I could add to FTCD, if that's a golden rectangle, right? That would be the largest square size I could add to it, 4 plus 2 radical 5. Wait a minute. Isn't this 4 plus 2 radical 5 over here? Since that's a square, that white one. All right. Okay. Well, if that's the case, what's the length from the top of this figure down to the bottom? In other words, from A down to D. Well, following the same reasoning, we could add those two pieces together, and we would have what? 4 and 3 is 7. Plus what? Well, 2 radical 5 and another radical 5 would make 3 radical 5s. So 7 plus 3 radical 5. So I contend that I have a large golden rectangle here made up of these pieces from this figure whose length is 7 plus 3 radical 5 and whose width is 4 plus 2 radical 5. Let me just circle those again. This is its length. This is its width. If I divide those two numbers out, I should get phi, if this is indeed a golden rectangle, right? So let me write those down again. 7 plus 3 radical 5. I'm going to divide that by 4 plus 2 radical 5. Okay? And I want to see if I'm going to get phi. Okay, to do this, why don't you write that down? 7 plus 3 radical 5. And write down underneath it 4 plus 2 radical 5. And now what we're going to do is we're going to take the calculator that's in this film, all right, and we're going to use it to compute that. Now this calculator is very similar to the ones that we used before. So I have to reshare my screen here. So give me a second to do that. So I'm going to do a new share, and I'm going to hopefully find the calculator, which is down here. Okay, and that's going to come up now. Okay. So now I am going to do the following. I'm going to do 3 times radical 5, and I'm going to add to it 7. That's the top of this fraction we're trying to work out. Are you ready? So here we go. I'm going to do second. No, not that way, I'm not. Guess I better do it this way. All right. Second All right, x squared, to get the square root of 5. I put it in there, and I hit enter. There's the answer. I'm going to multiply that by 3. So times 3 equals, I've got that answer. And now I'm going to add to that a 7. So plus 7, enter. There's my answer. Would you please write that down on your paper? 13.708204. We'll round the 6th decimal place off to a 4. Okay? Now we're going to compute the bottom. Okay, so you've got that written down, hopefully. So now we'll compute the bottom. So here we go. So I'm going to clear the calculator. I'm going to do the square root of 5 again. So second, get rid of this, delete that. Second, x squared, so square root of 5, enter. Now, as you remember, the bottom was multiplying it by 2, so times 2, enter. All right, I got that value, and to it, I'm going to add 4, plus 4, enter. You notice I got 8.4721359. So I'm going to make that a 3/6. 0.472136. Okay, so in my calculator now, I'm going to divide those two answers that I obtained. So I'm going to clear this out. I'm going to divide 13.70824. I'm going to divide it by, I'm going to divide it by 8.42. Oh, I'm sorry, I've got to put a 7 in there, right? I'm going to go back one. So I'm going to do a 47235. Okay, and I'm going to hit enter. Notice what I get. 1.618034, the golden ratio. So what have I just suggested to you that we can do now? Okay, so we want to do a new share. Let's go back to this figure. All right. All right. What I've suggested is the following. If you have a small golden rectangle, such as this one in green, and you add to it the largest square, which again I'm coloring in green, you have formed a new golden rectangle. That largest square was put on the side that makes up the length of the original figure. If I take the green golden rectangle and I add to it in red the largest square along its length, I contend that I get a new golden rectangle. Okay? If I take a golden rectangle, and of the largest square possible and add it to the length of my new red golden rectangle, okay? Up here, this will become red. And as we have just proven, we get another golden rectangle. So you can work in the opposite direction. You can suck out the biggest square and the rectangle left over will be golden. Or to any golden rectangle, you may add the largest square possible to its length side, and you will have formed another new golden rectangle. All right, terrific. Hopefully you understand that, okay? Great. All right, now you're about to look at the concept of taking a quiz. And the quiz is called Quiz 19. Let me get this up larger again so you can see it better. Okay. What do you have to be able to tell somebody or prove to someone to show that these are indeed golden sections? Well, remember, there are 3 things you have to be able to tell them. You have to be able to show them that the short piece, CD, plus the middle length piece, EF, have to add up to what? The length of AB. So those lengths must work out. Then what else do you have to be able to tell them? You have to be able to show them or prove to them that the middle length segment, EF, divided by the short segment, CD, will give you the answer phi. And you also have to be able to show them that AB's length divided by the middle length segment's length, EF, also has to give you phi. So those three principles have to be satisfied in order to say that those three segments are indeed golden sections. All right, look at this golden rectangle, please. Notice I am coloring in red this special triangle. What is true about that special triangle? It is called a golden triangle, probably because it was used to construct a golden rectangle. And what are the principles that you have to be aware of that exist in a golden triangle? In a golden triangle, the length, which you see here is 2, has to be twice the width down here, 1. I really said that wrong. They're the legs of the triangle, okay? Not the hypotenuse. The hypotenuse, of course, is over here, okay? But the two legs have to share the relationship, not length and width. The two legs have to share the relationship that one leg is twice the length of the other. Then you have what is called a golden triangle. It has to also be a right triangle. You're going to need to know that in this upcoming quiz. Okay, so we have got all the prerequisites finished for you to hopefully do well on quiz 19. If you have not completed quiz 18 yet, make sure you also do that, okay? Make sure you also send those down to me. Send them via text, just the answers, you know, like 1 is A, 2 is C, 3 is D, whatever they are, okay, with your name clearly on there so I know who it is that is texting me. So you got to tell me who you are when you send the text, okay? So this completes the last video section of today's class. And what I would like you to do, please, is make sure you send me all those things in the email, if you have not sent them already, that I have requested. I hope you have a great day. There is no assignment that you have to do before Thursday except to get those quizzes to me, okay? And Thursday, we're going to start yet another chapter in what we're talking about involving all this stuff with these golden figures. I hope everything goes well for you till Thursday. We'll see you then.